So yes, as you said, I will follow the topic of Zoe, talking about femoral angles too, but this time from an ontogenetic perspective. So in humans, the bicondylar angle and the neck shaft angles and femoral cross-sectional properties are developmentally adaptable and influenced by functional loading through ontogeny. Both femoral angles and the cross-sectional properties are also influenced by physical activity levels, nutrition, and other factors like hormones. If these factors affect both femoral angles and the cross-sectional properties, we expect to see a significant correlation between these variables through development. Since pelvic configuration primarily affects the femoral angle and the proximal femur in general, we focus on the femoral midneck cross-sectional properties. Moreover, the femoral midneck is a femoral location that has received less attention than the femoral midshaft or the shaft in general. Thus, in we study, we try to delve deeper in into the developmental path of this femoral location. As the development of bipedal locomotion is a crucial period for these two femoral traits, our main aim is to evaluate the relationship between the femoral angles and the femoral midneck cross-sectional properties during ontogeny. To do that, we analyzed 53 unfused femora belonging to a medieval population from Burgos, housed at the Laboratory of Human Evolution, and the age was estimated through the dental development, with the sample, covering ages between 2 to 20 years old, as the femoral neck start to develop at this concrete age, at 2 years old. The bicondylar angle is defined as the angle between the longitudinal diaphyseal axis and the sagittal plane perpendicular to the distal metaphyseal plane. To measure it, we took anterior view photographs of femora, import them into AutoCAD for tracing, and establish reference point on the metaphyseal surface. The image is then rotated to align the distal metaphyseal surface horizontally, allowing for the drawing of the longitudinal diaphyseal axis. Finally, the angle between this axis and the metaphyseal plane reference line is measured. The neck shaft angle, on the other hand, is the angle formed between the longitudinal diaphyseal axis and the cervical axis of the neck. Its measurement also utilized anterior view photographs, so we didn't do more photographs on the posterior view. And the process involves tracing the diaphyseal axis, drawing lines connecting the upper and the lower edges of the femoral neck, calculating 3 midpoints, and drawing a perpendicular line to the proximal metaphyseal surface. The angle is then measured at the intersection of the diaphyseal neck and the diaphyseal and neck axis. Both measurements employ AutoCAD tools for angle calculation and are taken from the anterior view to minimize the effect of femoral antetorsion variation. Importantly, this study ensures comparability between measurements of fused and unfused femora, as we included individuals until 20 years old. And this comprehensive approach allows for accurate and consistent measurement across a range of femoral developmental stages in which we are interested during ontogeny related to the development of bipedal locomotion. On the other hand, the femoral midneck cross-sections were obtained from CT scan using mimic software, and we measure the total area, the cortical area, the medullary area, the second moments of area, the polar second moments of area, section moduli, polar section modulus, and theta. The sample was sorted then into 4 age groups according to locomotor and adolescent development, and all the variables were age standardized using linear regression, the ordinary least squares regression, and the standardized residuals were then used to perform the Pearson correlations among them, both for the total sample and for the sample divided by age groups. Well, you can see here some, not only on the femoral midneck, but some individuals belonging to each group that we use. In this case, we exclude adults because at the femoral midneck, there is a shift in the alignment of the moments of inertia, so we decide to exclude them and focus only on ontogeny. So the bicondylar angle, we can see that it increases from birth to 6 years and then stabilizes or decreases during the juvenile transition and increases again during adolescence. Conversely, the neck shaft angles exhibit a more dynamic pattern of change than the bicondylar, and it sharply decreases from birth and throughout infancy, remains stable during juvenility, increases significantly in early adolescence, and decreases in late adolescence. Then, after controlling for age by examining the age standardized residuals, no significant association is found between the neck shaft angles and the cross-sectional properties. Nonetheless, we observe a significant correlation between the bicondylar angle and the second moments of area, in which you can see in the left side, and the maximum and minimum second moments of area that you can see on the right side. During early adolescence, the bicondylar angle decreases slightly, as do the second moments of area, while the maximum and second moments of area increases. This implies that in the adolescent transition, a shape change of the femoral midneck cross-section is accompanied by a decrease in the bicondylar angle. These results suggest that age groups with relatively greater cross-sectional properties of femoral midneck do not always show lower neck shaft angles values, and that despite the variation in body proportions across age groups, the extent of neck shaft angle decline is likely similar among individuals with comparable gait and walking patterns. Thus, although the neck shaft angle and the cross-sectional property appear to respond to different stimuli, the bicondylar angle and the cross-sectional properties seem to be interrelated, at least during ontogeny. This may be as a consequence of the patellar expansion and the enlargement of the medial condyle of the distal epiphysis that occurs during adolescence. So in future research, we hope to expand this analysis to the whole diaphysis and explore if this relationship is the same or not at the different levels of the shaft, for example, the most distal section of mid-shaft or the subtrochanteric region. So to conclude, just let me extend my gratitude to the Laboratory of Human Evolution, the scientific and organizing committee of this year, and the project of the Spanish government that allows that support financial and economic resources to this to take these studies. Thank you.